Okay, let's get going. We're going to talk about significance testing. This is inferential statistics. Regression and correlation have enough little tools in the toolbox that we can get a little distracted just learning them all, and we don't realize that for all of them, or for most of them, it's just like the other stuff that we've been learning. There's an inferential part and a descriptive part. We've been talking about what you can do descriptively with regression and correlation, just how to describe what's actually going on in your particular data set, in your sample. But now we're going to move to what we always do, just like with the other procedures for t-tests, ANOVA, chi-square, stuff like that. We're going to talk about some procedures for trying to come up with good estimates for what's going on in the population as well. Another way to say that is, how much do we trust that this model we built from this sample is reflecting something real, something that's going on beyond just this little sample? So it's the same question we have before. We know what we have in our sample. How much do we trust that this is coming from the population? How much can this tell us about the population? So you could think of what we've been doing so far as these four questions. First, this descriptive stuff. What is the best model for describing the relationship between x and y, between our two variables, in our sample? Just looking at our sample, not thinking about anything beyond our sample. And that's where we come up with the correlation coefficient. That's where we come up with the regression equation. And then we think, how good is the model? How well does that model fit the data? Now, this might seem like an inference thing, but it's not. This is still description. The model itself is just a simplified version of what's going on in the data, and it's never going to fit perfectly because it's overly simplified. There are reasons to do that, and they're very good reasons. A simplistic model can be very useful in many circumstances. But that's not the same as inference. This is still descriptive statistics, determining how well the model fits the data. And we use R squared and residuals and the R to kind of tell us how well the model fits the data. We're still just working in our sample. That model itself is theoretical, but it's not a population thing. It's just in our brains. It's just an abstract type thing. And we're saying, how well does this model that we've built fit this particular sample? So then we're going to talk about how we can use the model to do some prediction. Not in this lecture, but the next one, or a couple down the road perhaps. And then we're going to ask how much we trust the model. And we're going to do some statistical significance testing. So that's what we're going to talk about right now. We're going to talk about significance testing. We'll talk about prediction later because we don't always do it. It's not that common in psychology. So these hypothesis tests, we can test the significance of all of the pieces of regression. We could test the significance of A. In other words, the null hypothesis is that A in the population is 0, that the y-intercept is 0, and then the hypothesis, the alternative hypothesis would be that it's either greater or less than 0, so it's not equal to 0 in the population. But we don't usually care, because I mean, who cares? If you think about this, it rarely makes sense to care whether the y-intercept is 0 or not. It's just a description of what's going on. It's not better or worse if it's 0 in most cases. This is just in a few rare cases that we care. However, software will always test this for you. R will test this for you, and you always see. Now B, here we care, because B and R are the same thing. Remember, B is just like R in disguise. R is like Super B. R is standardized B. B is R with its Clark Kent suit and glasses on. So if you test the significance of B, you are also testing the significance of R. If you get a p-value for R, it's the same as the p-value for B. So you don't test them both. If you test one, you've got the test for both. The software usually does all these things for you. It's pretty automatic. And I'll talk about the mechanics, but I'm not going to ask you to calculate that in this particular course. So what is the meaning of that kind of thing? Well, it's rarely of any interest to test a null hypothesis that A equals 0. But this is very interesting to test the null hypothesis that B equals 0. Because if in the population the slope is 0, in other words, the correlation coefficient is 0. If the slope is 0, then the correlation coefficient is 0. If the slope is positive, then the correlation coefficient is positive. If the slope is negative, then R is negative. So if the slope is 0, that means there is no association in the population, and we're just kind of whistling in the wind here. We're making a big deal out of nothing. We're making a big deal out of a relationship that showed up in our sample, but only because of some fluke of random sampling, which is what we're always concerned in. How likely is it, if the null hypothesis is true and there's nothing going on in the population, and for correlation that means if there's no correlation in the population between X and Y, then how likely is it that we would see the data that we see here? If there's a high likelihood, then we don't want to trust our data. So if B is not statistically significant from 0, your model is not a very good model. Don't use it for things don't trust it. So now we're going to move on to talking about this concept of population correlations. Check out this graph. This symbol up here, I don't know if you can even see my mouse moving on the screen here. This symbol up here is rho. Rho equals 0.95. There's rho equals 0.7. Rho means population correlation coefficient. There are two. Each variable has a sample and a population version, right? So if the values in the sample of x can be correlated with the values in the sample of y, well then if you had all the values of x, there would be a particular correlation with all the values of y. It wouldn't always be a strong correlation, it wouldn't always be a weak correlation, it would be whatever it is. It would be the actual relationship between x and y in some true population type sense. And so I tried to simulate that using R, and I think there's something like 100,000 or 10,000 data points here or something to say this is what a population would look like. This is what a correlation coefficient of 0.5 looks like. You can see we're getting close to a shotgun blast. We're getting close to a shapeless blob here. 0.5 isn't as strong as we sometimes think in the social sciences. 0.3, that's looking pretty blobby to me. 0 is just a circle. Now I don't know if this monitor resolution is doing the right things to make that a nice circle, but here, hang on, maybe I can force it to. Well, according to my monitor, it's the right resolution, but I don't know if I trust it. Anyway, this should be a circle. This should be a nice circle, just blob in the middle of your screen. Now, negative 0.3 is a little more ellipsoid, negative 0.5, negative 0.7, negative 0.99 is very nearly a line. Now, the first time I showed this a couple of years ago, after I was very excited that I made all these slides, one of my students asked me to do this really fast and said this would be really great for a rave at a nightclub. Said this would be really great background to dance to. I don't know, I think I can see it, yeah. Maybe some 1980s techno pop. Alright, so the big question as always, which of those populations did our sample correlation come from? So in correlation and regression, which population correlation, which pattern of association between population variables is reflected in our sample? So our sample is telling us about what's going on in the population. What relationship in the population created the relationship we see in the sample? Same question as before. We look at something in our sample and say, where did you come from? You just showed up on my doorstep. Where did you come from? Same as before. I think of samples as like little lost kittens. We have to figure out where they came from. So, let's think about this a little bit. About these significance tests. The null hypothesis is important to think about. It takes a little bit of a mental leap, a little bit of mental practice to kind of get this in your head. If the null hypothesis is true, we're always going to have a null hypothesis, rho equals 0. So, if the null hypothesis is true, then whatever we see in our data, in the population, there is no correlation. So this is what the correlation looks like. So let's look at what happens, how it's possible that there could be no correlation in the population, and yet we could see a correlation in our sample. So what you're seeing here, I hope you can see the gray. If you can't, there should be bazillions of little gray dots all over here and a few dark red dots. I think there's like 100 dark red dots or something. So what I've done here is I'm showing you the gray dots and the dark red dots put together. There's a correlation of 0 between x and y, between the x-axis down here on the bottom and the y-axis over here vertically. There's a correlation of 0 between them. However, I've carefully selected, using the magic of R, a few dots in here, and the correlation between those dots, that's the sample, is 0.1, despite the fact that the correlation in the population is 0. So you see the gray dots here. The gray and the red together are a correlation of 0. So I'm showing you a situation of what happens if the null hypothesis is true. There is no correlation between these two variables in the population. In a true sense, there is no correlation. However, random sampling happens to have given you this pattern of dots so that when you do the calculations or run through R and figure out what the correlation between the red dots themselves is, between the variable values just for the sample, just the red dots, you will find a correlation of 0.1. And you would find a slope like that, a regression line like that. And here's the same thing with a correlation of negative 0.1. Same thing. There's still no correlation in the population. Now here I've selected some randomly selected dots to find a correlation of 0.3, even though there is no correlation in the population. The null hypothesis is true here, because there is no correlation in the population. But random sampling gave us these reddish-orange dots here. And so those reddish-orange dots do have a correlation between them. The two variables are correlated at 0.3, even though they were selected from a population that had a correlation of 0. Or we could imagine selecting dots, these blue ones, from a population that had no correlation between two variables, but we just happened to select just the right dots so that there is a correlation among the blue dots of negative 0.3. And this is what it would look like for 0.5. If we selected a sample that was correlated at 0.5 from a population that was correlated at 0, that there was no association, or negative 0.5. And here we selected the dots for 0.7. I hope you can see it. It's increasingly unlikely. These red dots here are taking on a nice ellipse shape. For 0.7, it's pretty clear. It's pretty pointed. So it's unlikely that that would happen by chance. Just like anything else, if you have a correlation of 0 in the population, it's unlikely that truly random sampling would give you some dots, or n equals 100, that the correlation was actually 0.7. That you would actually select observations that showed a correlation between them that was this strong. And the bigger the n, the less likely that is to happen. So that's getting pretty strong. And you can see negative 0.7 if we selected just the blue dots randomly on accident. It can happen because random is random. Random selection is random, so anything can happen. So we're interested in the likelihood of that happening. So this is the null hypothesis situation. Now, 0.9. How likely is it that you would select just those dots? Dots that lined up so nicely in your sample that these observations, when you ran the numbers on their x and y values, gave you a correlation of 0.9. It's extremely unlikely with 100 dots. With like 5 dots, it's pretty likely. But with 100 observations, it's not very likely. Here's a negative 0.9 situation. So this is always the situation that we're in when testing the significance of R. And remember, testing the significance of R is the same as testing the significance of B. So if you've done a hypothesis test and you have a p-value for R, then you have the p-value that mostly matters for most of regression and correlation. That's almost all we really care about. For simple regression and correlation, we just test R or B, either one, because the outcome will be the same. The null hypothesis says that there's that shotgun blast in the population, rho equals 0. And so we've got this sample. And here's what happened in our sample. The alternative hypothesis, it could say rho is not equal to 0 or less than 0, greater than 0. So just like everything else, it can have a two-tailed or a one-tailed negative or one-tailed positive alternative hypothesis. But let's say it's a one-tailed positive hypothesis. So our alternative hypothesis is that the true population correlation is positive. That's all it is. We don't even commit to anything more. We don't say it has to be like 0.9 or 0.7 or something. We just say it's positive. We're pretty weaselly and wishy-washy about that. And we've been rightly criticized for not getting better null hypotheses. But this is what we do. We say rho is greater than 0. So let's put that same sample data right there. Well, if the null hypothesis is true, then this is where that sample data came from. That sample data was just sampled. I didn't get all really careful and awesome with this. I just put two graphs on top of each other. But just to help you imagine, then this sample data came from a situation where the null hypothesis was actually true. These sample data were just selected, and they happen to have some sort of association with them, whatever association is that these green dots show, even though they came from a population that had no association. Whereas if the alternative hypothesis is really true, now I picked some correlation like 0.7 or 0.6 or something like that. If there is an association, then these green dots come from something that has a positive association to it. So we have to decide which is more plausible. Do our green dots, are they more likely to have come from this population or this population? And we're going to do that reverse logic where we don't really answer that question. We just say, if this shotgun blast null hypothesis population on the left is really the truth of where these dots came from, then what's the likelihood that we would have seen these dots, that we would have gotten a correlation coefficient this strong in our sample if there's no correlation in the population? And then if the p is less than 0.05 or 0.01 or something, then we reject that hypothesis and we say, well, the situation on the right must be what's happening. So the null hypothesis is almost always that rho equals 0. The alternative hypothesis can be one or two-tailed. As you see here, you can be thinking it's either a positive or negative correlation, two-tailed, or it's a negative correlation or it's a positive correlation. And R has such a weird distribution that you have to kind of transform it before you can test this, but as soon as you transform it, everything gets super easy. It's just a really simple t-test. It's simpler than any t-test you've done so far, actually. You have to do essentially like a tenth of the work of a normal t-test. The degrees of freedom are always just n equals 2, and you can plug it into one big formula. Now I give this to you even though we're not going to do this calculation in this class. We're out of time. Maybe next year if we have some more time, but not right now. I just want you to understand this is very, very easy. Look, there's only two things in that formula. There's an n and there's an r. It's squared in the denominator, and it's not squared, but it's just r and n. Those are the only two things you need to know. You just need to know the correlation coefficient and the number of observations. And that's it. You calculate t, and then you just use a regular old t-test, and you just look up your t-value, and you look it up for n minus 2 degrees of freedom, whatever that is, and for your alpha level, whatever that is, and for one or two-tailed, just like you did for all the t-test stuff. If you can do a t-test, then you can do this 5 times. This is so easy. But remember, we're not going to do this in this class right now. Maybe next year. So we test the significance of R because there's a sample value, which is an estimate of a population value. The test looks just like this. We have an estimate in the sample minus the null hypothesis estimate over the standard error. Like I said, don't worry about the details, but it follows the same pattern we've seen so far. And once you've transformed R into a t-value, then you can test everything in the t-distribution. So I'm just almost copying and pasting graphics from back in the t-test chapters. The standard deviation of this distribution. This is the distribution of all possible correlation coefficients that could happen if the null hypothesis was true, if there was no correlation in the population. But all those correlation coefficients have undergone that little mathematical transformation to turn them into t-values. So the standard error is the standard deviation of this distribution, of the t-value of R. So the null hypothesis, as you see in this row, if I didn't make it too faint, way over on the left, the null hypothesis says that there's no correlation in the population, and yet somehow you ended up with a strong negative association. Or if you go a little further right, the same thing. You've got no correlation in the population. All these little graphs are the same gray shotgun blast. But then as you go from left to right towards the center, you see that the null hypothesis is saying there's no correlation. But if your R value, T value falls at these points, then what must be happening is that you just happen to select some random points that gave you that kind of a correlation. And then from the center out to the right, again, you're having a stronger and stronger correlation in the sample, despite the fact that there was no association in the population. So this entire row that you see here, H0, is what must be happening if the null hypothesis was true, depending on where, left to right, on this graph you find your results. The alternative hypothesis, I'm playing a little fast and loose with null hypothesis testing here, but you can say the alternative hypothesis is that one of these distributions actually describes what happens in the population here. So our null hypothesis is that t-value of R is 0 in the population, and it's let's say it's a two-tailed test. We put our t-values for R critical. Now, if we have a value way over here on the right, then this must be what's happening. So we've got this in our sample. We find that GDP growth after economic aid in this example, the correlation value is 0.52, and we have this regression equation, negative 2.05 plus 0.24 times the aid in billions of dollars equals GDP growth of countries. And our observations are a bunch of different countries, these dots you see here in the plot. So there's our association. There's the best fitting regression line. Our correlation is 0.52, so we turn that correlation of 0.52 into a t-value. If our observed t-value is over here, then we reject the null hypothesis. But what if our observed t-value was here? What if the correlation was only 0.18? Well, then we would not reject the null hypothesis. It would not be a strong enough correlation for us to reject the null hypothesis. What about here? I have a different correlation there. Now the correlation is negative 0.23. Well, not quite. We wouldn't quite reject the null hypothesis as if this was our data. Same hypothesis and everything, but we wouldn't reject it if our data didn't give us a strong enough correlation coefficient. But let's say there's a nice strong one. Look at how well that line is fitting those dots. So our correlation is negative 0.76. We have a very strong correlation, and we do reject the null hypothesis. Our t-value is like, negative 4 or something like that. So this is kind of the way things work. The strength of the correlation coefficient, which is also the strength of B, just transformed, determines whether you have a significant result or not. So we're not going to do this in class. R does it for you pretty instantly. And remember, there's always a test. It's always your sample estimate minus the null divided by the standard error. Remember, R does it for you. Remember, the results of testing the significance of B are the same as the results of testing the significance of R. Although, if you want to do this by hand, doing B, you actually do some different math, but you will end up with the same p-value. So it doesn't matter which you test, B or R. Or R squared, you can test that too. It doesn't matter. The significance will end up being the same, the p-value. So our output, if I tested the regression of y on x, so x predicting some y, I didn't give these variables names except x and y. This is what you're looking for your intercept, as we've seen before. That's A, and this is B, the estimate for the coefficient or estimate that's on the row for whatever the independent variable, the predictor variable is named, is B. And then down here you see the t-value for the significance test of B, which is the same as the t-value for the significance test of R, and the p-value. So very, very small. That's the smallest that some R distributions can recognize. So 2 times 10 to the negative 16th. You could just look at the little asterisks. Check it out. 3 asterisks. Awesome. Statistically significant. So the correlation between those two things is statistically significant. That asterisk means less than 0.001. The p-value is fairly small. So there's also a test for A, but we don't really care. I mean, in this case, the line must have gone pretty close to the 0 point, and so it wasn't statistically significantly different from 0, the y-intercept, but we don't usually care. And notice that the legend even tells us what blank means. Blank means 1, which is R's way of telling us no stars greater than 0.10 or something. So anyway, what happens to the significance R of R as the sample size increases? Now, you should be able to figure this out, but let's just go through it anyway. It shouldn't take too long. There's the degrees of freedom for the t-critical. And it's also in the numerator for t-observed. So here's n equals 18. It's a very strong correlation coefficient. Oh, it's a capital R. Why did I do that? So if we calculate this out, you put 18 in the numerator there, and that gets multiplied eventually. You have a t-observed of negative 7.06. So the t-critical is much smaller, so you definitely reject the null hypothesis. Now what if the n was only 8? So we have a correlation coefficient that's really similar from a data set we've seen before, the car price and fuel miles per gallon, efficiency miles per gallon. And when you test this significance, now you only have an n of 8, t observed of negative 3.79, and with this smaller degrees of freedom, you have to look at a different t critical, and if we chose alpha equals 0.01, we wouldn't quite make it. Oh, yes, we would. We would barely make it. So sample size, as everywhere else, makes a big difference. If you want to find statistical significance, get a big, big, big sample. It's the lesson with pretty much everything. Now let's do a quick review. There's a few more little lectures that I'm going to try and get done for this class, but let's just do a quick review of some of the stuff we've got going here. We first try and find the best model of our relationship between x and y in our sample. We're going to use a linear equation, which is all we learned for this class, although there are lots of curvy and funky models out there. If the conditions are met, we create that linear equation or a line on a graph, and that's our model of our relationship. It's a simplified way of understanding our relationship. We find B for that, we find A for that, we interpret B and say for every 1 unit increase in whatever, we expect blah 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 change in whatever. So every once in a while we interpret A, but that's kind of rare, only if there's a good reason. So once we've got that model, we've described the relationship in the data, and we've given it kind of a simplified model. We've usually calculated R. And R squared are what tell us how good that model is. So B can't really tell us how good that model is. You need to standardize B and turn it into R, or R squared, even better, because it's easier to understand, and determine how good that model is for describing what's in our data. The closer those data fall to a straight line, the better the model is at describing the data. And so if you have small residuals and a big R and a big R squared, you have a really good model, a model that describes the data well. If you have small R squared, and big residuals, then you don't have a very good model. Now sometimes we use the model to predict new values, which we're going to do in a different video lecture here. If the model fit is good enough, we do that. If it makes sense to do it, we do that. If we need to, we do that. But sometimes we just really don't. We need to be careful of extrapolation. And then we almost always go to this point. We calculate confidence intervals of F or B or R, and we perform a significance test for B or R, and then we're usually pretty much done. So that's regression in a nutshell. As you've seen, the nutshell contains quite a lot of little chunks, and I hope you're still with me for the next one.